Main objectives of today's session are: why do we need classification, Dobrenius triads, Newland's law of octaves, Lothar-Meyer volume curve, Mendeleev's periodic table, modern periodic table, and IUPAC nomenclature of elements with atomic number greater than 100. The arranging of elements into different groups systematically on the basis of similarities in their properties is called classification of elements. The classification of similar elements into groups makes the study of the elements easier. There are about 118 different elements known so far. The earliest attempt to classify the elements was grouping the then known elements, about 30 elements, into two groups, metals and non-metals. The defect in this classification was that it had no place for metalloids. Metalloids are elements which have properties of both metals and non-metals. The elements were first classified by French scientist Antoine Lavoisier in 1789. He classified the elements into metals and non-metals. The demerit of this classification was that metalloids were not included in the classification. The second classification of elements was done by John Dobrenius in 1829, called the Dobrenius triads. In 1829, he classified some elements into groups of three, which he called triads. The elements in the triad had similar chemical properties and orderly physical properties. Dobrenius classified the elements in the increasing order of their atomic masses into groups of three elements called triads. In each triad, the atomic mass of the middle element was approximately equal to the average atomic mass of the other two elements. The first triad consists of three elements: lithium, sodium, and potassium. Second triad consists of calcium, strontium, and barium. The third triad consists of chlorine, bromine, and iodine. The atomic masses of elements of first triad, lithium, sodium, and potassium, are approximately 7, 23, and 39 respectively. It is clear that the atomic mass of the middle element, that is sodium, is the average of atomic mass of the first and the third element, that is lithium and potassium. The demerit of this classification was that all the known elements at that time could not be correctly arranged into triads. The third classification of elements was done by John Newland in 1865. Newland classified the elements in the increasing order of their atomic masses into groups of 8 elements called octaves, like the notes of the music. Newland found that when the elements were arranged in the increasing order of their atomic masses into octaves, then there was a similarity in the properties of every 8th element. This means that starting from hydrogen, the 8th element is fluorine. Thus, hydrogen and fluorine will have similar properties. Similarly, starting from lithium, the 8th element is sodium. Thus, lithium and sodium will have similar properties. Starting from sodium, the 8th element is potassium, and from potassium, the 8th element is copper, and from copper, the 8th element is rubidium. Thus, all the elements arranged within the same vertical column, like lithium, sodium, potassium, copper, rubidium, etc., will have the same chemical and physical properties. The demerits of Newland's law of octaves are: he could arrange elements only up to calcium out of the total 56 elements known. All the known elements and elements discovered later could not be correctly arranged into octaves. That is, after calcium, every 8th element did not possess properties similar to that of the first. This periodic table did not include inert or noble gases because they were not discovered. Some elements having different properties were placed in the same row. For example, cobalt and nickel having different properties were placed along with chlorine, fluorine, and bromine. Iron having the properties similar to cobalt and nickel was placed in a different row. The third classification of elements was done by Mendeleev in 1869. It was called the Mendeleev's periodic table. Mendeleev classified the elements in the increasing order of their atomic masses and similarities in their properties. The formulae of oxides and hydroxide formed by the elements was also the basis for the classification of these elements. Mendeleev's periodic table has 6 horizontal rows called periods and 8 vertical rows called groups. The groups 1 to 7 have 2 subgroups called A subgroup and B subgroup. Group 8 had 3 rows of elements. Elements having similar properties were placed in the same group. There are some spaces left vacant in the table to accommodate the elements to be discovered in future. Thus, according to Mendeleev's periodic law, the physical and chemical properties of elements are periodic function of their atomic masses. The merits of Mendeleev's periodic table are: elements were classified on a more fundamental basis of their atomic mass and properties. Spaces were left vacant to accommodate the elements to be discovered in future. It could predict the properties of elements which helped in the discovery of new elements. The inert gas elements discovered later could be placed in a separate group without disturbing the table. Mendeleev left spaces for elements to be discovered later and even predicted the properties. He named the elements as Eka boron, Eka aluminium and Eka silicon, which were later found to be scandium, gallium and germanium respectively. The demerits of Mendeleev's periodic table are: some elements are not arranged in the increasing order of their atomic masses. Cobalt is placed before nickel and tellurium is placed before iodine, etc. The position of hydrogen is not clear because it shows properties similar to metals as well as non-metals. The position of isotopes of elements is not clear. In 1913, Henry Moseley modified the Mendeleev's periodic table and arranged the elements in the increasing order of their atomic numbers, and this is called the modern periodic law. According to the modern periodic law, the physical and chemical properties of the elements are periodic function of their atomic numbers. In the modern periodic table, elements are arranged in the increasing order of their atomic numbers in the form of a table having 7 horizontal rows of elements called periods and 18 vertical rows of elements called groups. The modern periodic table is shown here. According to the modern periodic law, the properties of elements are periodic function of their atomic numbers. In the modern periodic table, elements are arranged in the increasing order of their atomic numbers. The elements are further classified into periods and groups. The vertical columns are called groups and the horizontal rows are called periods. The elements belonging to the same group will have similar properties. For example, lithium, sodium, potassium, rubidium, cesium and francium are the elements belonging to the first group, and all these elements will have similar chemical and physical properties. The modern periodic table is also called the long form of the periodic table. According to the modern periodic table, the elements are arranged in the increasing order of their atomic numbers. It explains the position of elements in relation to the other elements. It consists of groups and periods. The vertical columns are called groups and horizontal rows are called periods. There are 18 groups and 7 periods, and the elements belonging to the same group will have similar properties. On the basis of the nature of the subshell in which the last electron of the atom enters, the elements are divided into 4 blocks. They are the S block elements, P block elements, D block elements and F block elements. First we will discuss about the S block elements. In these elements, the last electron enters the S orbital. The S block element comprises of group 1 and group 2. Group 1 metals are called alkali metals and group 2 metals are called alkaline earth metals. The general electronic configuration of group 1 elements is NS1 and that of group 2 is NS2. For example, lithium, which is a group 1 element, the electronic configuration is 1s2, 2s1. On the other hand, beryllium, which is a group 2 element, the electronic configuration is 1s2, 2s2. All the elements of S block are metals. They have low ionization energy and low melting and boiling points, and they are electropositive elements. The compounds of S block are mostly ionic and colorless. For example, the common salt NaCl, which is a compound of sodium, is colorless and is an ionic compound. It is made up of Na plus and Cl minus ions. Next is P block elements. In these elements, the last electron enters the p orbital. The general electronic configuration is Ns2, Np126. For example, nitrogen, which is a group 15 element, the electronic configuration is 1s2, 2s2, 2p3. The p block elements comprise of elements belonging to group 13 to group 18. These elements are non-metals. They are electronegative and form covalent compounds. Next is d block elements. In these elements, the last electron enters the d orbital. They are also known as transition metals. The general electronic configuration is N-1d 1 to 10, Ns 1 or 2. For example, the outer electronic configuration of nickel, which is a group 10 element, is 3d8 4s2, where N equal to 4. The d block comprises of elements belonging to group 3 to group 12. They show variable valency and have high melting and boiling point. They form colored compounds and have catalytic properties. Next is F block elements. In these elements, the last electron enters the f orbital. They are also known as inner transition elements. The general electronic configuration is n-2f1 to 14, n-1d 0 to 1, ns2. They are present below the periodic table in two rows. They are called lanthanides and actinides. Lanthanides are elements named after lanthanum. Actinides are elements named after actinium. They have high melting point and boiling point. Metals are present on the left side of the periodic table. They are solid, malleable, ductile and conductors. The nonmetals are present on the right side of the periodic table. They are solid, liquid or gas. Metalloids are present in the zigzag area between the metals and nonmetals. Examples are boron, silicon, germanium, arsenic, antimony, tellurium. The demerits of modern periodic table are: it is unable to include lanthanides and actinides in its main body. The problem of the position of hydrogen in the table has not been solved completely. The configuration of helium is different from inert gases but are placed in the same group. Now we will discuss the nomenclature of elements with atomic number greater than 100. Each digit of the atomic number has got a distinct name and a corresponding abbreviation. 0 is represented by the name nil and its abbreviation is N. Similarly, 1 is named as Un, 2 bi, 3 tri, 4 quad, 5 pent, 6 hex, 7 sept, 8 oct and 9 n. The abbreviation is simply the first letter of the name. The name of the element is the digit name followed by the suffix ium. For example, the element with the atomic number 115 will be named as unpent followed by ium, so unpentium. The first letter of the symbol will be in capital letter, so the symbol of 115 atomic number is capital letter U followed by small letter u and p. The nomenclature of elements with atomic number from 101 to 118 is given here.